The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
I would like to introduce the fourth topic, and the speaker, Mike Buckley of Halsall Associates, will be presenting the leveraging structural BIM to increase efficiency. Mike Buckley is a national practice leader for structures at Halsall Associates. He's with the firm for about 25 years and acted as a principal on structural engineering projects ranging from very small $20,000 to over $1 billion in Canada and overseas. Mike has been the principal on some of the largest projects in Canada using BIM, including Humber River Hospital project. He has experience in many building types, from institutional, commercial, industrial to residential, recreational, entertainment. He also commonly asked to peer review projects where Halsall Associates was not the engineer of record. Halsall, so I would like to introduce Mike Buckley and call him to present his topic.
Thank you, Neb. When I was in university more than 30 years ago, I was constantly being ribbed by the mechanical, electrical, and mining engineers saying, you're not going to have a job because there's software out there that will design entire buildings. Well, I can tell you, and Neb can tell you, and another colleague of mine in the audience can tell you, well, it's been almost 30 years and I'm still very much overemployed because we can have all this wonderful software, these tools and whatnot, but it doesn't work unless you have the appropriate people who are geared to teaming and collaboration. And with that, I'm going to move on. I'm going to talk about implementation, BIM workflows, what I think the future of BIM is, and some case studies. You'll have, as like to be the case, I'm third, so there's been some of my points talked to about already, so I'll be very brief about some of those things. At Halsall, I think we look at BIM as a very different set of systems. Everybody's talked about Revit or Navisworks so far this morning. We consider BIM as any tool or modeling tool that we use to develop information besides just structural sizes and elements. So we've been working, I would say in a BIM kind of environment for a long time. In fact, we were the beta test center for Revit in Canada, Revit Structures in Canada. But, Neb and I worked on projects, including this one here, where we used the models of various forms to look for clash issues. This happens to be a very complex system where there are trusses spanning one direction and another set of trusses spanning perpendicular to those trusses and nested in between one another. So you can imagine the potential for clash scenarios there. Another project that also worked on, very complex. Again, this is pre-Revit days, pre-Revit structure days, but there was an integration between our design models, the fabricator's drawings, the architectural massing models, and everything else. And you can look at the complexity of that node of connections and can imagine how difficult it would be as a structural engineer to review the connection designs for those elements without being able to look at these things in 3 dimensions. And then also understanding that, well, a bolt was X. A bolt was predefined to be of a certain size and grade, and et cetera. So we could not have built this building without having models. There are a number of ways that you can use models. But we have a lot of projects where nobody else is using Revit, for example, except us. And the constructors use our models independent of everybody else to do studies on various things. But once you're into a model that is transportable between systems, anybody can take it and probably use it to some very good use, like the mechanical trades, for example, as opposed to just a flat set of documents that is typically and still used as defining what the contract parameters are, per se. Implementation challenges. If you are really wanting to model a building properly, you have to pull your work forward dramatically. And that means everybody needs to pull it forward dramatically. One of the struggles we have as a structural engineer is mechanical engineers not doing their work until very late in the project, and architects continuing to design through time and space when we're actually building the projects. Humber River Regional Hospital, for example, is over 1.6 million square feet, and we were awarded the project, and we're in the ground within building the foundations within about 3 months of getting the project. So a lot of work has to be done ahead of time, and models need to be built in order to send it. So the black basically indicates where we should be focusing all of our efforts in terms of building models and developing details. Unfortunately, I think in the sort of BIM world at this moment, designers and to some degree constructors are working on that green line where a lot of the work is still happening way too late in the project. So it all needs to be brought back to be much earlier in the project if you're really going to be successful. BIM workflow breakdowns, you see the Alice Dawn presentation talked about this. This happens to be a Penn State version of that. We've used these to various degrees on projects, defining who's responsible for what and where and when. But here it goes back to the people again. You have to set up appropriate first of all, you need appropriate people leading the project at various levels. You need collaborative individuals, not people who are going to, like computer geeks who want to sit back and just work on stuff. They have to be able to communicate. If you don't have people who can communicate on the phone, by email, or in person, you won't have very much success. We've worked with different kinds of models. One, the traditional method where you have linked models. There was a discussion about the structural engineer having a model because he wants to control the design system structurally. The architect having their model because they want to control geometry. Well, when you have that kind of thing going on, there's a lot more effort going into coordination, and you have a lot greater risk for problems being set up. So ideally, everything is up there, it's coordinated, everything's in its right place. If you're not watching out, what can happen? Somebody moves a slab edge, and all of a sudden you have nothing lining up. Maybe the shelf angle is correct, but the beams and the reinforcing of the walls and all your reinforcing shown where it's supposed to be isn't actually where it really needs to be anymore. You can generate clean views of elements to see, bathroom looks like a bathroom to most people, but to structural engineer it can mean a whole lot of stuff, one of which is a lot of depressions in your slab that you have to consider for in your design. So if you have rules set up by setting up a particular workflows at the beginning that the architects define these spaces appropriately in their model, we can very quickly define what it means to us structurally. If you're dependent on one another's, zero tolerance modeling is absolute. We have old-time, I would call them draftspersons. They've been around long enough that they drew everything by hand, and they would plug it in by hand. And so when they went to AutoCAD, many of them would just spot it and plug it in as opposed to using an insertion point. Well, you can't do that. You have to have people who are committed to using the tools properly and inserting a column at a exact location, which can, be handled or managed through appropriate significant figures, and be, for all intents and purposes, within a zero, plus or minus zero tolerance. And you can see this happens to be a project where we did a model and the architect imported our model and relied totally on our model. And so you can see our model layered in behind their model. Ideally, when you're in a large project, is you want a central model, but that creates some issues. Again, who controls what from a geometry standpoint? We try to set it up so that we control and own columns, walls, footings, that sort of thing, and the architect needs to talk to us, negotiate with us, let's say, to if they need to move it. There are lots of advantages of having a central model. This is just a picture, and Dan Newfoglees will know that this is a project where we're the only consultant on the project using Revit for it, but it leads an opportunity for elements to be defined and gives an opportunity for the constructor to understand what he's going to be looking at when he comes to build the building. When we get into true integrated collaboration, you need a lot of computing power. We have clients that we work with around the world using these systems. There's accelerators, riverbed accelerators that work nicely to speed up packet delivery between one another. But Autodesk, for example, has Revit Server, which enables that even more positive collaboration time frames of what stuff is moving in and out. We do have a client who doesn't want to use Revit Server for whatever reason, and we check out pieces of the model and check it back in. It shuts your communication down by lots and lots of time, because if you're sending something over a busy set of DSL lines, it takes time for a central server, let's say in Edmonton, to answer you back in Toronto. What's the future? Again, a lot of people involved. We're not going to disappear. Generative design, laser scanning, 3D holograms in terms of client engagement, presenting things, 3D printing, something we call augmented reality. Normally I would show this to you in a video, but I'm being old school, don't necessarily trust the software, and that videos don't always work when you do presentations. So you'll see what can happen. This happens to be Lansdowne Stadium in Ottawa, which is a combination of a timber structure, which the architect defined the elements in Rhino, and we built a model that would using Grasshopper, which would translate and modify their initial Rhino model to certain densities of elements. So these are timber frames, main timber frames, that then have secondary elements that create a bit of a screen system on it. And if you adjust those, you see those sliders moving, the density of those elements change, and it's instantaneous in the model. You can play with it. This is only one level of something that you can do. Anyway, this turns out this is what the finished product is going to look like, integrated within the Revit model of the concrete structure in behind. Here's a sort of a R&D project that we're doing internally to do a little bit more broader linkage between different modeling BIM level pieces of software. And the reason we're doing this is because we like to have control over the interface. A lot of the software suppliers will tell you that we're totally compatible in talking, that SAP will talk to Revit or whatever. I will tell you that even embedded within Revit is Robot and their own analysis systems they even internally with their own systems have trouble talking to one another in implementation. So as structural engineers, we're very, I would say, anal about control over what talks to what and how those discussions take place. So This, we sent a gentleman out to buy a clamshell, and we peppered it up with little black dots so it would be a little bit more contrast, took a bunch of pictures of it, uploaded it to Revit servers, which generated a surface and a point cloud, which we then brought into Rhino to produce surfaces, and then used Grasshopper to create linkages to develop a structural framing system, for example, and link that to run back one way to Rhino and another way to our analysis software. So again, we can change details. In this case, the number of ribs in the shell, changing the shape. And each time we do that, the amplitude and the shape of the trusses change. And you do that, it automatically updates your SAP model, updates your Rhino models, and you can analyze these things in real time. Changes in the truss depth. Laser scanning. So this is we had a professor at the University of Waterloo go down to a project we're doing in Windsor in an armories building that we're converting for the university into a new teaching facility. These are all laser scans of the elements. And what we wanted to do was see, if you could laser scan the building, because we're changing the load on the building, and those trusses that you see on the right hand side of the screen, we have to analyze them. Well, we had them all measured and mapped out by hand. We wanted to compare, for example, how accurate the laser scans would be. And so you see the photo image of a connection, you see a laser image of a connection, maybe a little more close. What we found was, for the dimensional elements, let's say the angle, size, and depth and position, we are within 2% accuracy on those things. We're not quite at enough accuracy that we could pick up. If you look at the lower picture, the point cloud, you'll see two angles back to back. It's not quite accurate enough yet for us to get the thickness of those angles, but we're close. So from an architectural or existing building implementation, or a as-built or under construction, and this is what the point of the research at the University of Waterloo is, what is the under construction progress going on? How is it? How accurately can you have real-time presentations of what's been constructed, and where you may be able to use a little bit more class detection, not only within from using the consultant's information, but also using what's built. 3D holograms, you can print these things and set them up, and you can walk around the building. Those all be developed based on your models. 3D printing, University of Waterloo Nanotechnology Building, we modeled the connections, has a laser printer picked up. That just happens to be a piece of street furniture, that the chair there that an architect was developing for Waterfront Toronto for fundraising purposes. Augmented reality, it's just another way of looking at your model. You can, using webcams and plates that your computer recognizes, projects a 3D image on your computer screen, and your client can actually just rotate this piece of paper and lift it around and whatever and get his own idea of what's going on. So it makes that interface with your model for a less sophisticated client, for example, or whoever, a little easier. I'm not sure what sort of time do we have. 2 minutes. So unfortunately, a bridge that we did it was supposed to be done in timber, didn't get built, went on the shelf because the whole idea was to help attract more people to the waterfront of Toronto. However, some of the people who live on the waterfront of Toronto don't want people attracted to the waterfront, and very politically astute, and they happen to have this thing canceled on us. Well, the point, there were multiple pieces of elements of framing that had to collect at points, and we set up whole fabrication systems using our software so that all the prefabrication could take place. Managed Dual Tower, this just happens to be a Revit model on the left, a ETABS model on the right. But what we really, there were very complex link beams between the core walls, and concern over reinforcing placement and that sort of thing. So when it really boils down to it is we're communicating the construction in a sense to the builders using the Revit model, but boiling down to more even refined details, making sure that constructability of certain complex elements is in fact able to be achieved. Toronto Western Hospital is another example. The element down at the bottom is a situation where we had a post-tension beam with a lot of tendons that had to be strung between structural steel trusses, and the constructor was concerned that that was not going to work. So we built the Revit models and showed them that it in fact did. This is Humber River Regional Hospital. You'll hear a lot about this thing in the coming future. Well, mostly because it's Canada's first digital hospital, but there's so much concrete going into this thing that it's, I can't tell you that the volumes of concrete are just incredible. The raft alone is something like 150 or 60,000 cubic meters of concrete or something like that. Almost as much as in the raft of this hospital as in another hospital we built in another, as a whole hospital. So, but it's 1,000 feet long. We're building it without construction joints or control or expansion joints. The whole we're using it in our office to check quantities. We don't model reinforcing. We say how much reinforcing is going to go into a thing by cubic meter, and then we check against the volumes that are being poured.